All right, the next speaker is Professor Janolin, who can talk about the control of hysteresis through polar defects. Yeah, I'll give you a warning at 15 minutes. Yeah, you want 5 minutes.
Well, thank you, Peter, for the introduction. So, yeah, do you hear me in the back? Okay, apparently not even in the front. Do you hear me now? Is it a bit better? Okay. So this is the preliminary results that my PhD student, Janolin, had on what he wants to do on the control that he wants to have over the hysteresis loops. The control we want to have is not the one that has been developed over many years on soft or hard hysteresis loops, but rather, can we induce a double hysteresis loop? Can we shift a hysteresis loop along the axis? By how much and how reproducibly? So this is what we are going to do. And the idea is to use the symmetry-conforming principle, which is based on what was called in the 90s the volume effect, in which we are going to use acceptor doped ferroelectrics, creating, therefore, oxygen vacancies, and that will create defect dipoles that we are going to try to modulate in directions in order to influence the electric field that we are going to get in ferroelectrics. The dipolar defects align with the intrinsic dipoles and therefore provide a mean to alter the natural ways that these dipoles would evolve. The alignment being done through oxygen vacancies motion. Therefore, we will have a defect dipole that will be much heavier, and therefore that will be insensitive to the electric field that we will apply, and that will have a dynamic that is completely different from the intrinsic dipoles. And the effect we're going to either use or try to avoid is aging. And as many of us would say, aging is no degradation. There's a clear difference between the two. Aging is the ability to modify with time a property under the influence of an extrinsic source, whereas degradation is simply the loss of a property without even the existing external stimuli. And this volume effect was in competition for some time with another effect explaining the influence of the oxygen vacancy that was called the boundary effect, where it was thought that the oxygen vacancy were migrating into the domain walls. But as this aging has been shown on dielectric properties, even in single crystals, monocrystal monodomain, it was preferred over this boundary effect. So the symmetry-conforming principle actually extends this volume effect not only to ferroelectrics, but also to martensitic transition, explaining the rubber-like behavior of these alloys, and simply state that the defect symmetry will eventually, at the thermodynamical equilibrium, conform to the crystal symmetry, rather the other way around. By doing so, in ferroelectrics, we have the chance that they provide a restoring force for domain switching, and therefore provide a way to modify this PE loop. The idea is the following. At high temperature, when you have an acceptor dopant, you will induce oxygen vacancies that will statistically occupy the 6 possible positions around this dopant. This leads to a non-polar cubic symmetry of the defect dipole at high temperature. Whereas when you go down to ferroelectric phase, you will alter this statistical occupation, thereby favoring the apical position in the direction of the displacement of the dopant, resulting in a polar symmetry of your dipoles, of your defect dipoles. So the idea that was put forward by Ren in 2004 was that you start in this cubic phase where you have no intrinsic dipoles, no defect dipoles. You cool it. You have the ferroelectric domain that appear, but the oxygen vacancies continue to statistically occupy all of the possible sites, and only after aging do you have the appearance of a defect dipole that align with the polarization in the domain in which it lies. And therefore, if you cycle through field, instead of having a single hysteresis loop, as excuse me, as the defect dipole will not be altered by the electric field that you apply, they will provide a restoring force, closing the hysteresis loop at zero field. So this is what he wanted to do. And his take actually was to apply that to do some energy storage device. We considered initially 3 types of material: paraelectrics and materials with a single hysteresis loop or double hysteresis loops. And the idea was, how does aging affect these 3 types of structure of reaction of the material with respect with the focus of energy storage. So if you look at paraelectrics, the effect of aging being to reduce the dielectric constant, it would decrease the slope here, thereby reducing the quantity of energy that you could store. That was clearly not something that we wanted to have, especially in something that should last for some time. However, if you look at hysteresis loop, then you can see that indeed you can store a little more energy, but the effect of aging is actually beneficial in the sense that it is known for quite some time to shift the hysteresis loops. Thereby, with respect to time, we would be able to store more and more energy until the stable thermodynamical state would be achieved. And the bias electric field, the one by which your hysteresis loop is shifted, is actually increasing with the log of time, instead of, for paraelectrics, the dielectric constant decreasing with the log of time. And the other thing that we were interested in was the pinching of the hysteresis loop, simply because the quantity of energy that you can store is much larger. Okay. So in addition to this double hysteresis loop, another interesting aspect about these materials would be to look at the electrostrain that you can induce. And of course, you have the corresponding double hysteresis loop. And you can actually get this way very large strains. Still from the same paper by Ren, you have this deformation that is rather large, 0.8%. But what is mostly interesting is the field that is being used, which is only 200 volt per millimeter. And if you want to compare that with the relaxer ferroelectric single crystal, this curve here actually ends up being this almost straight line up here. So from an application point of view, you do not have to apply much of an electric field to get a very large strain, which is exciting for many people. Okay, so his take was, I'm going to substitute my barium titanate with something, and he chose copper. Copper is slightly larger than titanium in the coordination set. It's not stable in coordination 8, but we don't really care because on the A side it's coordination 12. It could occupy the coordination 12, but then if it were, the perovskite structure would not be stable. So the copper has also the benefit of having only mostly stable valence 2+. So by using copper, we were not having to worry about whether we would have multivalences or not on the B side. And we were pretty sure that it would stay on the B side. In addition, as copper is 2+, whereas titanium is 4+, it creates a neutral defect, thereby not introduce mobile charges inside our material, which should remain insulating, and we'll see that this is the case. And of course, it creates a defect dipoles, because the oxygen vacancies tend to stick around the copper, especially at the temperature that we are going to look for, that is below the Curie temperature. So a little tour of the kitchen. He did that through Mecano-synthesis. It is not the usual way that you would do barium titanate, but the advantage when you put 0.4% of copper inside your barium titanate is that you ensure that you have a rather good homogeneity of this dopant, because the last thing you want is to have all of your copper clustering at some point and creating a metal insulator composite. So he went through ball milling, and then the usual steps resulting in various ceramics with composition between 0.4 and 2%, but I'll stick with the 0.4% here. The densities are okay, 92%, no open pores, and despite starting with nano powder, after sintering, we get rather large grains. We get the pure perovskite phase with a preferential orientation 001 that is still a bit of a mystery to me, but that does not really affect anything. So the dielectric properties look good. We've got the TC we expect, and the second transition toward the orthorhombic phase. Afterwards, we do not see any relaxer character that is sometimes induced by the doping on the B site. And in addition, we do not see I apologize for the absence of the losses here. But you can see here that the losses are rather small at high temperature, meaning that even just above TC, we don't have much conduction going on, which is a good thing. So when you measure a hysteresis loop on these samples, after having made them, you get these hysteresis loops. Being interested in antiferroelectrics, I would have loved to be able to measure this type of hysteresis loops on many of them. So you can do that, and you can increase the maximum field that you apply every single time. You see that you have the effect of the defect dipoles being randomly oriented inside your material that bring back your polarization to a zero net polarization at zero field. And the IV curve are pretty clean as well, and you can also see that we still do not have any conduction going on, noticeable conduction in the IV curve here. So we were pretty happy with that, because it means that by simply putting just a little bit of copper inside your barium titanate, you could have a double hysteresis loop instead of a single one. But after having been through the pain of diluting properly your copper inside your barium titanate, if you, in the end, decide that you prefer to have a single hysteresis loop, you can still do that. All you need to do is cycle over this for more than 10,000 times. This is the evolution of these positive and negative polarization, because if you zoom, they are not exactly the same. And what you see is that up to at least 10 to the power 4, there's not much changes. After that, you clearly open your hysteresis loop. And once you have brought back this single hysteresis loop in a fatigue measurement that is similar to the hysteresis relaxation that you have in magnetism, you get a single hysteresis loop that is stable for at least over 2 weeks. And then Jiasheng was a bit frustrated because he thought that these hysteresis loop did not look as good as the double one, and he wanted to get it back. And the only thing that he could do, after having heated it above TC and brought it back to room temperature, was to get this blue curve here that is indeed pinched, but not as pinched as the initial double hysteresis loop. So we did not have the full reversibility in that way. So the idea was, well, maybe the temperature at which we went was not high enough, so we went to TC plus 100 degrees for 2 hours, 10 hours, 20 hours, and indeed we could get a beginning of a pinching, but clearly not the double hysteresis loop very nicely closed over here. So Jiasheng, being not easily discouraged, decided what the maximum temperature I can go to, and he went to TC plus 600 degrees Celsius. And this time he stayed there 2 hours and did not change much the overall shape of the hysteresis loop. 20 hours, still not pinching completely the hysteresis loop. And then Christmas break happened, and he decided to leave it just below TC for 2 weeks, actually. And in that case, we get a loop that is way more pinched than what we had at high temperature. And the only difference between the black curve here and the red curve here is that the maximum field that we have applied for this measurement is not as high as this one. So in order to have the full reversibility of the aging effect, you do not need actually to go to very high temperature for a very long time, staying underneath TC in the ferroelectric phase, effectively for 2 weeks, but I think we can stay a much shorter time, enables the pinching of the loop to be back. So we have some control over the double loop or single loop. Now we wanted to shift this hysteresis loop. And we wanted to shift for example, the single hysteresis loop. So what Jiasheng did was that he heated the sample above TC for 2 hours and then quenched it and measured the hysteresis loop. And the idea here was to have a reference point where we want to make sure that the polling that we will do afterwards is reversible and can be erased. So this step here is a kind of reset. And then he reheated it to the same temperature for 2 hours, pulled it, field cooled it, and measured the hysteresis loop. And what we see is that what he sees is that the hysteresis loop is shifted. Reheating, quenching, the hysteresis loop comes back to its original position. You do that and you repole it at higher field and so on and so forth, and you shift slowly the hysteresis loop that you have pulled and field cooled. So by a simple pulling of the defect dipoles at high temperature and through the phase transition, you can shift this hysteresis loop along the field axis, which has been a known effect of aging for a very long time. Okay, and that, if you remember that he was interested in energy storage, is a good news, because at the energy storage density that you are interested in is this corresponds to this area. By increasing the polling voltage up to 2 kilovolt, he got an increase of the stored energy density by 48%, which is significant considering the amount of work it takes to do that, which is not much. So this is about all we have to present for now, and all we know is reproducible. That is the ability to go from a single loop to a double loop, the ability to shift a hysteresis loop under electric field, leading to an increase in energy storage density. So alliovalent doping seems to be an effective way to gain control over these PE loops. It seems to be also a possible avenue for energy storage. Nevertheless, the interaction between the ferroelectric domains and the defect dipoles need to be refined to have a better control and to be able to do some engineering of these defect domains. And we still need to look into more details about the stability over longer times, over the limits by which you can shift this hysteresis loop, how you can tell piezoelectricity also that way, in order to go a bit further with that. And with this, I'll thank you for your attention.
Questions?
Thank you. Yeah, I find that fascinating. So how many of these defects are sitting on the grain boundaries, and how many would diffuse if you have domain boundaries inside? How many would over this period of time diffuse underneath TC along the grain the twin boundary?
So from about the position of the copper inside the sample, the EDX that we have done showed that it is evenly distributed. We haven't been able to see any particular concentration of copper inside the grain boundaries, and we do not see any increase in the dielectric losses that would somehow show an increased conductivity of the grain boundaries. From the literature that exists on barium titanate doped with copper, people who have done EPR have found also that copper tends at these doping levels, low doping levels, to sit majoritarily, if not completely, inside the grains and not at the grain boundaries. So the Rietveld refinement that we've done is consistent with an amount of copper that is of the order of what we put in. It's not a quantitative probe. So I am reasonably confident that copper sits inside the grain. and not at the grain boundary.
And do they diffuse later if there's a boundary, ferroelectric boundary?
We do not see any difference in the conductivity in the dielectric constant. So that's the only insight I have. It's not a definite answer I can provide you with.
Okay, thank you.
Any other questions? Oh, thank you.
Yeah, I really like this and your results, and I think I understand it. So one thing, I think if you don't go to as high a field, then you may not see this fatigue effect. So it's, if you didn't do the full, switching, but you just went over to where you have the high piezoelectric response and with some bias field and just sat there, it'd be very interesting to me if you could put on a bias field and sit at that strong response point, and then just do small oscillations around there and see how long that would last.
Absolutely, but the other thing that one needs to take into account is that in application, for example, if one of the application of antiferroelectrics as electrostrain is to make high pressure actuators for valves, for example. So it is a unipolar cycle that you would do anyway. So you would not necessarily flip defect dipoles, and therefore I don't expect the aging under unipolar solicitation to be as strong as we would have.
Have you done that?
We are doing that, and the first results show that it is indeed way more stable, but we want to be able to do that on several samples just to make sure before claiming anything.
All right, if there are no more questions, let's thank the speaker again.